Okay, so we're back with our friend, the spring mass system, and we have the general differential equation used to solve these types of systems in front of us. So I just want to go give a quick reminder of what all these terms mean. So we have this term here is like the motion and the acceleration of the object. We have this damping term here, which, like we said in the last video, had something to do with air resistance. It's working against the motion. Here we have the spring force, so this is just due to the nature of the spring wanting to contract back in. And then finally, on this right-hand side, we have some outside force. So last video, we only talked about the case when this was equal to 0. So what we did then was we just assumed that our system was completely isolated in some sort of box here, and no one was touching it. We saw that we got some pretty nice results, and in regards to like exams and stuff, a lot of it was just looking at this table to see exactly what your solutions of y are going to exactly look like. But what we're going to do today is we're going to focus on the cases where f of t is non-zero. So we have some outside force here that is being applied to our mass, and we're going to see exactly how that changes our function of y here. But our mass by itself is just moving up and down. If we didn't have this outside force, it would just go up and down for forever. So it doesn't really make sense to apply a force that's like constant or increasing with time. It really only makes sense to apply one that's periodic, so that we still get this nice up and down motion here. So what we're going to do in this course is we're going to constrain f of t to be periodic. So it's going to be really big in some cases, 0 in some, really big in the negative direction in other cases, and so forth. And so the book defines this. We define f of t as some amplitude f naught times cosine of omega t. So this right here is the amplitude, and this omega here is the frequency of oscillation. So this will dictate how fast this force is being applied. If it's going rapidly up and down like that, this is not a great way of representing it. Or if it's going, slower like that, this omega dictates that here. And we've seen this omega before. We've seen omega naught is square root of k over m. That came up in the last section. But what we need to be very confident here is that omega in this force oscillating term here is not necessarily equal to omega naught. That's not even close to spelling that. General. So omega and omega naught are different. They come from different things. This k and the m come from the system itself, right? The spring and the mass itself. And then this omega here comes from the frequency of the applied force. So two completely different things here. And so what happens, and we'll see, is a lot of our solutions actually depend on if this is true. They depend if the frequency of the force oscillation is exactly equal to the frequency of the completely isolated oscillation of our system. Okay, so let's just proceed how we did last time. So we have a couple cases, right? We have the case where there's no damping. And we saw that that was when c is equal to 0. So that means there's no air resistance or anything. It's just doing its own thing. And so that corresponds to this equation. I'll just write it down real quick. And this is, not equal to 0 this time, but equal to the some outside force that we're given. Okay. And what we have to do is we have to remember that our solution to this, when we don't have 0 on this side, is going to be our complementary function and our particular solution. So our complementary function, remember, solves the homogeneous differential equation, and our particular solution is going to take care of this non-zero term on the right. We've learned that a lot of this has to do with just guessing what this particular solution is going to be. So this section is really just telling you how to guess what this particular solution will be. Okay, so It tells us from last section the complementary function, what solves the homogeneous differential equation. You've seen this before. A naught cosine omega naught t minus phi. And remember we said omega naught was square root of k over m. Okay. And then our particular solution actually depends on omega. So it's going to depend on what this input omega is on the right-hand side. So there's going to be two cases that we're going to look at. So what happens if omega naught is not equal to the omega that we stuck in on the right? So if they're oscillating at different frequencies, what's going to happen here? It tells us that, and this is a really long solution here, and I'm going to get rid of this for a sec because we don't need it yet. From the book, if you want to know where this came from, consult the textbook. They do a pretty good job of figuring out or explaining where this came from. But I'm going to write it out here so we can talk about what's going on. So we have this first sine term, which is the difference of the two omegas divided by 2, and then we're going to take the sum of those two omegas divided by 2. And we're just multiplying, that's like a coefficient to this t right here. So what we have here is this is like the solution. This is what the textbook tells you your y of t will look like. So what does this motion actually look like? Well, we have two different signs here being multiplied together. So we first have this one here and this one here. So you'll notice that the coefficient here is smaller than the coefficient here. So what this tells us is we're going to have two different modes of oscillation pretty much. So if I draw the motion here, time going along the horizontal axis and then the height, we have something that looks like this. So we have a change in oscillation. And then you can see this oscillation itself, or the change in it, actually oscillates over time as well. So we have this curve here, looks something like a sine curve, right? That corresponds to this solution, this part of the solution. And then this part here corresponds to this part of the solution. So we have these weird little pockets of waves that are moving around, and they're oscillating in two different ways defined by these two sine functions. So this is one of the cases we can have. We can have this cool little system that looks like this. And then we have the coolest case is when omega naught is equal to omega. And so what happens here is something a little spooky, but it tells us that our solution, just reading out of the textbook again, we have a naught cosine omega naught t minus phi, which again is just our complementary function. And then I have plus f naught over 2m omega naught t sine omega naught t. Okay, again, long solution, but you recognize this. This is our complementary function, and this is our particular solution. We add the two of them, and we're good to go. So nothing really is going on with this here. We've seen this before. But what's really important to see here is this t. So we add this t in there because we have that special case almost where we have repeated roots. So this kind of correlates to it. I don't want to get into too much detail, but we stick a t out in front of this. And what does that actually do? Well, as t increases, the sign here is bound, right? Sine is not going to get bigger than 1 or negative 1. And then this cosine here is also bound. So let me do it in blue. This is bound as well. So this first term will not be, this will be greater than or equal to, wrong side. This term up here, this whole thing, will be at most a naught, and it can go down to negative a naught as well. This term here, in fact, doesn't have a bound because we have this t in here. So t is increasing, which increases our amplitude, which increases how high our sine wave is going. So what we have here is we have time along this axis and the height. It starts off nice, but then it increases, and then, oh no, it just keeps going on and on and on. And it will never ever stop until your system breaks. And that's the important part here. So we have just this trajectory of increasing amplitude. And what's cool is this, well, it's not cool, but it's a problem. So you don't want your system to be doing this. You don't want your system to be going, stretched to its limit and then some. So this is a system that is being pushed past its physical limit and will break. So this is what we call resonance. When W is equal to, or omega is equal to omega naught. And it has a lot of consequences in engineering. So if you are an engineer taking this course and you're going to build something in the future, please don't build it with resonance. An example, if you want to look it up, is the Tacoma Bridge. What happened was they built this really cool bridge. It was really big. And then the wind started blowing, and the wind was like at the perfect amount of force to make the bridge start wobbling. And it was wobbling in the sense that it wobbled more and more as the wind kept blowing, and eventually it snapped. So that's a real world scenario where this came up. So yeah, just some motivation there. Don't do this if you're an engineer, please. And so this covers the cases where we don't have damping, okay? So we're either going to have resonance, which is bad, or we're going to have the case where we have this cool little wave pocket pattern, okay? And then damping, believe it or not, actually is easier. So C is no longer 0, and I'll just write down the equation again. If you hate seeing this equation, fast forward 10 seconds or so. All right, so we have this equation now, and we're just using, again, the same logic that my function here is going to be a linear combination of my complementary function and some particular solution. Our complementary functions are going to come from this table, which I hope moves up there in a second. Great. So this is where my complementary functions are going to come from based on the case that we're given. So again, if you remember from last video, we checked to see if c squared over 4km, its relation to 1, and we figured out exactly which of these three solutions, 8.5, 11, 12, and 13, we should be using to describe our system. So that's where y c of t comes from. And then y of p is a little weird. That's not very good. I'll write that again. Y of p is equal to f naught over h cosine omega t minus, I think it's nu. Okay, and h and mu are constants. So the textbook gives definitions. In fact, we'll use them in a second in our example. But they're constants, okay? So we just have some constant oscillation function going on here. That's our particular solution. So what we have, I'll do an example. So if we go through our problem and we find that we have underdamping, let's do underdamping. Then we can pick off our complementary function. So we have y of t is equal to e to the minus ct over 2m. And then I have c1 cosine of mu t plus c2 sine of mu t. And the mu is just a constant as well, given by the right-hand side. And then I have to add on my particular solution, f naught over h cosine of omega t minus nu. And there's just one more thing I want to point out here, and I know it's taking a while to get to this point. But let's look as time goes on. So as time goes on, we know that this term here will be bounded by C1, and this term will be bounded by C2. This term here will be bounded by F naught over H. But what we have here is we have this exponential term that's multiplying these terms here, my complementary function. So what I have is, as time goes on, you'll see this negative sign, which means that this equation here is getting really, really small. So as time goes on, this disappears completely. So physically what this means then is that if I apply some force with underdamping, if I apply some outside force in a case where there is underdamping already in my system, eventually what's going to happen is the outside force here is going to dictate the motion completely. So what this looks like is, again, time and position. I have it starts off oscillating a little bit weirdly, and then it just goes right into the oscillation defined by f of t. Okay, so this weird part up here is when time is small enough for this term here to matter. And as time goes on, we just saw this term dominates and it only matters after some specific point, okay? So what we do then is I'll write this one more time. We have our complementary function and our particular solution. This complementary function, because it dies off so quickly, it doesn't matter because of that exponential, we call it the transient term. And then this one, because it just is what happens to the system as time goes on, we call it the steady state. So your steady state is your particular solution because it dictates your system after a while. All right. So what we'll do is we'll do a quick example so I can just show you what it looks like on an exam. If this was a good enough summary for you, by all means stop the video, but there may be people who want an example. All right, so sorry, just as another brief summary, we've covered all the cases. So we have damping. What I didn't tell you, I guess, is that underdamping it's no special. There's nothing special about it in this particular case, because if you look at 8.5, 0.11, 12, and 13, they all have that e to the negative ct over 2m term in front of them. So they're all subject to exponential decay in the complementary function and just being subjected to the outside force as time goes on. All right. So just as a brief review of what we need to be doing on exams, it's going to say something like find the transient and steady state solutions to some differential equation, and they'll just give it to you. So we have d squared y dt squared plus 2 dy dt plus 5y, not equal to 0 this time, but 4 cosine of 2t. All right, so what do? Well, we need to first find our complementary function. That's the first step in all of these non-homogeneous differential equations. You find the complementary function. So how do we do that? Well, we're given all the complementary functions. We just need to know which one to use. So we're going to look at c squared over 4km and figure out if we have underdamping, critically damping, or overdamping going on. All right, so again, using the trick where I just set m equal to 1, I have c equals to 2 and k is equal to 5. So c squared over 4km gives me 4 over 20, which is a fifth, which is less than 1. So I go up to my table or to my cheat sheet, and I say, okay, I have underdamping. This is the solution I need. So my yc of t is equal to e to the negative t c1 cosine of 2t plus c2 sine of 2t. So I just inputted this information into this solution here, and that's what we got. So you can check that on your own if you're skeptical. But that's our complementary function. What we have to do now is we need to find our particular solution. And so we go up and we say we know yp of t is f naught over h cosine omega t minus nu. And I never told you what h and nu were because I didn't feel like writing them because there are a lot. But h is equal to, just right from the textbook, m squared omega naught squared minus omega squared, that whole thing squared, believe it or not, and then plus c squared omega squared. That's h. And so if you plug in what we have omega naught is square root of k over m, which is square root of 5 from our information that we're given. We have omega itself came from this applied force here, so we know that's equal to 2. And then c is 2 as well, and m is equal to 1. So what you do is you plug all those in, you get h is equal to the square root of 17. And then we can use h to find eta now, or nu. So nu is equal to the arc cosine of m omega naught squared minus omega squared over h, which just gets really messy, honestly. But that's equal to the arc cosine of 1 over root 17. I might have done my math wrong, but I hope not. Okay, so we have our particular solution. We can put this all together. And so we have y of t is equal to complementary function plus the particular solution. So we have e to the negative t, c1 cosine of 2t plus c2 sine of 2t. And then we add to that 1 over h, which was root 17. No, it was f naught, sorry. So we have f naught over h. Our f naught in this particular case is 4. So we have 4 over root 17 cosine omega was 2. Omega t minus our phase shift, which was nu, which is arc cosine of 1 over root 17. Really lengthy here. So what we have to do is we just know that this equation here, because it dies off as time goes to infinity, is our transient solution. And then this solution here, because it survives, because there's no exponential, is our steady state. And that's your entire part here. Sometimes I'll ask you to solve for C1 and C2 with initial values, but that's kind of a pain. So if you have a forced oscillation, normally it's just determining if it's damping, determining what type of damping you have, and then finding these transient and steady state solutions. Sorry this video got pretty long in the end, but hopefully this will be helpful.